13.3 Analysis Model. Particle in a field, gravitational. The outline of this video is as follows. We will begin by exploring a historical and conceptual puzzle known as the problem of action at a distance. This is the question of how objects like the Sun and Earth can exert forces on each other across vast, empty space without being in contact. Next, we will introduce the gravitational field as the modern solution to this puzzle. The central idea is that a massive object does not directly pull on another distant object. Instead, it alters the properties of the space around it, creating a field. Following that, we will provide a precise mathematical definition for the gravitational field, relating it to the force experienced by a test mass. We will also learn how to visualize these fields using diagrams of field lines. Finally, we will work through a few examples to solidify our understanding and see how to apply the particle in a field model to solve problems involving gravity. While Newton's law of universal gravitation was a monumental success, accurately predicting the motions of planets and comets, it presented a deep conceptual puzzle for scientists of his time. This puzzle is known as the problem of action at a distance. The core question was, how can two objects, like the Sun and the Earth, exert a force on each other across millions of kilometers of empty space? There is no physical contact, no rope or string connecting them. How does the force get from one object to the other? Newton himself acknowledged this difficulty and could not provide a mechanism. This fundamental question about how forces can act over a distance was a major challenge that motivated the development of a powerful new idea in physics, the concept of a field. To understand how gravity acts across empty space, we introduce a powerful idea, the concept of a field. A field is a physical quantity that has a value at every point in a region of space, and it is established by something we call a source. As an analogy, consider atmospheric pressure. The air itself is the source. Because of this air, every point in the atmosphere, whether at sea level or on a mountaintop, has a specific pressure value. This collection of all pressure values makes up a pressure field. Now let us apply this concept to gravity. For the gravitational force, the source is any object with mass. We will refer to this as the source particle and denote its mass with a capital M. This source mass fundamentally alters the properties of the space around it. The key takeaway is that a mass creates a gravitational field that permeates the surrounding space, ready to exert a force on any other mass that enters it. To make the concept of gravity more concrete, we need a precise way to define and measure the gravitational field at any point in space. The first step is to detect the field. We do this by placing what we call a test particle, which is simply an object with a known mass, m0, at the location we want to study. If that test particle experiences a gravitational force, we have confirmed that a field exists at that point. This observation leads directly to the formal definition. The gravitational field vector, which we represent with the letter g, is defined as the gravitational force vector, F sub g, that acts on the test particle, divided by the mass of that test particle, m0. It is crucial to understand that the gravitational field is a property of the source mass like a planet or a star and the space around it. The field exists at a point whether or not a test particle is there to measure it. The test particle is just our probe. In short, the gravitational field at a point is the gravitational force per unit mass that an object would experience there. This slide formalizes the particle in a field model, which explains how an object interacts with an existing gravitational field. We have already established the first step. A source mass creates a gravitational field, g, in the space around it. The second step, shown here, is what happens when we place a different particle with its own mass, m, into that field. That particle will experience a gravitational force. The mathematical representation for this interaction is that the force vector, F sub g, is equal to the particle's mass, m, multiplied by the gravitational field vector, g. This equation is the heart of the models. The power of this approach is that it separates the properties of the source from the properties of the object experiencing the force. The field G contains all the information about the source, like the Earth. The mass, m, is a property of the second object placed in that field. This means the force acts at a distance without any physical contact, which is why we classify gravity as a field force. We can now derive a specific formula for the gravitational field created by a source mass, like a planet. This allows us to calculate the field anywhere in space without needing a test mass present. We start with Newton's law of universal gravitation for the force between a source mass, m, and a test mass, m naught. The field, G, is defined as this force divided by the test mass. When we perform this division, the test mass, m naught, cancels out. This gives us the equation for the field from the source mass. G equals negative g times m divided by r squared, all multiplied by the unit vector r hat, which points radially outward from the source. The negative sign is important. It indicates that the field is attractive, always pointing inward toward the center of the source mass. For example, at the surface of the Earth, this formula gives a field strength of approximately 9.80 newtons per kilogram. Note that the unit newtons per kilogram is exactly equivalent to meters per second squared. The essential result is that the gravitational field depends only on the source mass that creates it and the distance from that mass. This slide presents figure 13.4, which gives us a visual representation of the gravitational field around a massive object like the Earth. The arrows you see are called field vectors. At any point in space, a field vector tells us two things. Its direction indicates the direction of the gravitational acceleration, and its length represents the magnitude or strength of that acceleration. On the left, we see the global view. The vectors all point radially inward toward the Earth's center. As you move farther from the planet, the vectors become shorter, showing that the gravitational field gets weaker with distance. The diagram on the right, however, shows a close-up view of a small region near the surface. Here, the field vectors are practically parallel and have the same length. This is what we call a uniform field. This approximation is extremely useful because it is why we can use a single constant value, g, for the acceleration due to gravity in most problems near the Earth's surface. This example demonstrates how we can use our knowledge of gravity to calculate a fundamental property of our planet, its average density. The key idea is to combine the formula for gravitational acceleration with the basic definition of density. First, we begin with the equation for the acceleration due to gravity at the Earth's surface, which is g equals the gravitational constant g times the Earth's mass, m sub e, all divided by the Earth's radius r sub e squared. We can algebraically rearrange this to solve for the mass of the Earth. Next, we recall that density, represented by the Greek letter rho, is defined as mass divided by volume. We will model the Earth as a perfect sphere, so its volume 5 sub e is 4/3 times pi times its radius cubed. By substituting our expression for mass into this density formula and simplifying, we arrive at a final equation for the density. It becomes rho sub e equals the fraction 3 times g over the quantity 4 times pi times g times r sub e. Plugging in the known values yields an average density for the Earth of about 500 kilograms per cubic meter. Let us consider a follow-up question to see what our result for the Earth's average density can tell us about its internal structure. Suppose we are told that the density of granite, a common rock at the Earth's surface, is about 2.75 times 10 to the power of 3 kilograms per cubic meter. We can now compare this surface density to the average density for the entire Earth that we just calculated, which was 5.50 times 10 to the power of 3 kilograms per cubic meter. Notice that the density of surface rock is only about half the average density of the whole planet. This comparison leads to a very important conclusion. For the overall average to be so high, the material deep inside the Earth, particularly in its core, must be significantly denser than the material at the surface. This is a powerful insight. Simple measurements of the gravitational constant g and the acceleration g can provide real information about the composition of the Earth's deep interior. Here we will calculate the weight of the International Space Station in orbit. This example demonstrates that an object's weight is not constant, but depends on its location in a gravitational field. The first step is to find the station's mass, which is constant regardless of its location. We divide its known surface weight, 4.11 times 10 to the power of 6 newtons, by the surface value of g, 9.80 meters per second squared. This gives us a mass of 4.19 times 10 to the power of 5 kilograms. Second, we calculate the gravitational field strength, g, at the orbital altitude of 350 kilometers. Using the universal gravitation formula, we find that g orbit is about 8.82 meters per second squared. As expected, this value is smaller than the g value at the surface. Third, we find the station's weight in orbit by multiplying its constant mass by this new value of g. The result is an orbital weight of 3.70 times 10 to the power of 6 newtons. So, the space station is not weightless. Its weight in orbit is about 90% of its weight on the ground, a direct result of the weaker gravitational field at that altitude. Let us now summarize the key ideas related to the gravitational field. The central concept is that any object with mass alters the space around itself by creating a gravitational field. This field provides the mechanism through which the force of gravity acts at a distance. We define this field vector, g, at any point in space as the gravitational force, Fg, experienced by a test particle divided by the mass of that test particle, m0. This definition leads to a very powerful tool called the particle in a field model. This model states that if you place an object of any mass, m, into a known gravitational field, g, it will experience a force given by the simple product Fg equals m times g. Finally, remember that the strength of the gravitational field created by a source mass is not constant. It gets weaker with distance, following an inverse square law. So the further you are from the source, the weaker the field becomes. Let us wrap up by considering two questions that test our understanding of weight and gravitational fields. The first question asks if it is accurate to describe an astronaut in orbit as weightless. As we saw with the space station, an object in low Earth orbit still experiences about 90% of its surface weight. The gravitational force is still very strong. The sensation of weightlessness occurs because the astronaut and their spacecraft are in a constant state of free fall, accelerating together toward the Earth. Therefore, the term weightless is not technically accurate. The second question involves a new planet with twice Earth's radius, but the same average density. We start with the formula for surface gravity. G equals g times m over r squared. The key is to express the mass, m, in terms of density, which we will call rho, and radius r. Since mass is density times volume, we can write m equals rho times the quantity 4/3 pi r cubed. Substituting this for mass, we find that g is directly proportional to the product of density and radius. Because the new planet has the same density but twice the radius, its surface gravitational field will be twice as strong as Earth's.